Is this organic compound a primary, secondary, or tertiary alcohol? We're supposed to give a reason for the answer. So let's go ahead and take a look. Right, so in compound A, let's just zoom in on compound A. We have 1, 2, 3, 4 carbons. So that should be butanol, right? We do have a branch here that I'm not accounting for, but we're going to take care of that. So let's take a look. Let me just circle that. This is our longest chain. We can take this as our longest chain. Even though if we go up, we would still get the longest chain of 4 carbons. Let's just take that as our longest chain. And then we have a branch on the second carbon and the functional group. Right, that is what we are dealing with. Let's go back to the question. Is it a primary, secondary, or tertiary alcohol? Well, this is a tertiary alcohol. So let me just write that down first and then explain to you why I'm saying so. This is a tertiary alcohol, right? Why do we say that it is a tertiary alcohol? It is because, take a look at these. This carbon that is bonded to OH. The carbon that is bonded to OH is bonded to 1, 2, 3 carbons, right? So if the carbon that is bonded to OH is bonded to 3 carbons, it makes it a tertiary alcohol. If it was bonded to 2 carbons, it would make it a secondary alcohol. And then if it is only bonded to 1 carbon, it would make it a primary alcohol. So right, it is a tertiary alcohol because the carbon bonded to OH is bonded to 3 other carbons. There we go. So that is 2.1.1. Let's take a look at 2.1.2. Write down the IUPAC name for the above mentioned compound. Okay, so like we have figured out, we have 4 carbons on our longest chain. So that is butane. And then which carbon is our functional group found? Well, if we start counting from the left, we have 1, 2, 3. But if we start counting from the right, we have 1, 2. So clearly we have to start numbering our carbons from the right. So we're going to have butane, 2, all. But we need to account for that branch there. We need to account for that branch. So on the second carbon, we have 2-methyl. So there we go. 2-methyl butane 2-ol. That is the IUPAC name of our compound A. 2.1.3. 2.1.3. The above mentioned compound undergoes an elimination reaction. Write down the structural formula of the product that is formed. Elimination reaction. So let me just write that structural formula without condensing it. So this is OH, and then hydrogen. We need another. Okay, here we have a branch, so let's put that there. And then elsewhere we have hydrogens. Okay, so which elimination reaction can an alcohol go through? Because this is an alcohol that you're dealing with, right? So the elimination that an alcohol can go through is dehydration. It is dehydration. The alcohol loses 1 hydrogen and an OH, right, making it H2O, hence dehydration. That is the only elimination reaction alcohols can undergo through, right? So it means that the structural formula of the major product formed should be an alkene, right? This question is very specific. Major product, right? We have a major product and a minor product for these reaction. We have a major, well, for the product of an elimination reaction of alcohol, right? Dehydration. We have a major product and a minor product. So this is just the alcohol. This is not the answer. This is not the answer. This is just the alcohol. We just draw in the structure of the alcohol so that we can better make sense of it. So the major product of dehydration that compound A will undergo will look like the following. So we have 1, 2, double bond, carbon, carbon. So there we go. And then hydrogen everywhere else, hydrogen everywhere else. So 4 bonds on that carbon, it is satisfied, and let's just fill out hydrogens everywhere. So let's check the number of bonds. This 1, 2, 3, 4. So everything is fine. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay, right. You have to calculate the number of bonds to avoid making any mistake. We also need our branch. I'm forgetting to put the branch here, because we have a branch here on the second carbon. So we don't have a hydrogen here, but rather we have a branch. So that is what we have. That is what we are dealing with. Let's check if the number of carbons is still intact. 1, 2, 3, 4. 1, 2, 3, 4. Okay, I'm happy with that. All right, let's move to the question that follows. 2.2, 2.2.1. Consider the organic compound B. 2.2.1. Define the term functional isomer. Okay, so compound B is pentane 3-on, so that is a ketone. But well, the question wants us to define the term functional isomer, so let's go ahead and do that. Functional isomer, organic compounds with the same molecular formula but different functional groups. Same molecular formula but different functional group. That is a functional isomer. And then 2.2.2, I'm expecting that the question is gonna have something to do with isomers. Write down the homologous series to which the above mentioned compound belongs. Okay, compound B. This is 2.2, and 2.2.2 is a sub-question of 2.2.2. Okay, I was starting to ask myself which above mentioned compound, because I was thinking 2.2.1, but it is compound B that we are referring to. So compound B is a ketone, but the name of the homologous series is actually not ketone. It is ketones. It is in plural, by the way. Yeah, it's one of those things that we usually overlook. But the name of the homologous series is not ketone. It is ketones. Yeah, if you go to your exam guidelines, that is exactly what you're going to find. You're not going to find the homologous series ketone. No, the homologous series is ketones, right? We're just being, more precise. We live in no stone unturned. Okay, that is 2.2.2. Let's do 2.2.3. IUPAC name of its functional isomer. So the functional isomer of ketones is aldehydes, right? The functional isomer of ketone is aldehydes, right? They have the same, a aldehyde looks very similar to a ketone, but the only difference is that the double bond oxygen is at the end. So here we have pentane 3-on. So the ketone that you're looking for is pentanol. That is, the aldehyde, not the ketone I meant. The aldehyde that we're looking for is pentanol. Pentanol and pentane 3-on are functional isomers. So what are we looking for? IUPAC name of its functional isomer. Oh, okay, we're done then. We're looking for the IUPAC name. I thought we were looking for the structure, right? But we're just looking for the IUPAC name. The IUPAC name is pentanol, right? 2.2.3. What about 2.2.4? Letter that represents its positional isomer. So we are dealing with pentane 3-on, right? So the positional isomer is pentane 2-on. It has only one positional isomer, right? Because we have 1, 2, 3, 4, 5 double bond oxygen, right? If you put this oxygen here, it is pentane 2-on. Same is true with when you put it here, you'll still have pentane 2-on, because we have to start numbering from the side closest to the functional group. So we're looking for pentane 2-on here on our table. Letter that represents is positional isomer. Okay, let's take a look. Pentane 2-on looks to be compound E. It looks to be compound E. Because take a look at compound E. We have 1, 2, 3, 4, 5. So that is where our pent is coming from. And then on the second carbon, double bond oxygen. So there we go, pentane 2-on. That is compound E. So the letter that represents is positional isomer. The answer is E there. The answer is E. It is compound E. Pentane 2-on. Write down the balanced equation using molecular formula for the complete combustion of compound F. So let's take a look at compound F. Compound F is 1, 2, well, not 2 anymore, but actually 3, right? So we have 5 carbons in total. We have 5 carbons in total. So that is C5. How many hydrogens do we have in total? We have these 3 here. We have these, which gives us 6. And we have 3. So that is 12, right? So H12. And then it is a combustion reaction. So it is excess oxygen to give us CO2 plus H2O. We just need to balance this equation. So C5, C1. What do? We put 5. In putting 5, the carbons are balanced. And then we move to the hydrogen. H12, H2. So we put 6. We put 6 in attempt to balance the equation. And now take a look at this. We have O2 here. And here we have 5 multiplied by O2, which is 10. Plus 6 multiplied by O2, which is 6. So this is 16. And then in order to get 16 on the left hand side, we must multiply with 8. So there we go. We have our balanced combustion reaction. Here we go. 3 structural isomers with molecular formula C6H14 are used to investigate the effect of branching on the physical properties of hydrocarbons. So I think just that statement answers most of our questions because we know that we are investigating the effect of branching on the physical properties. So we already have our independent and dependent variable in a way. But anyway, stories. 3.1, define the term melting point. So melting point is the temperature at which the solid and the liquid phases of a substance are at equilibrium. The temperature at which the solid and liquid phases of a substance are at equilibrium. That is 3.1. Let's take a look at 3.2. 3.2, write out the independent variable for investigation 1. Write down the independent variable for investigation 1. So let's go ahead and take a look at that. So investigation 1. Obviously, we are investigating the effect of branching. And then in our case, the physical property happens to be melting point. So is branching the independent variable or is melting point the independent variable? We have to define what we mean when we say independent variable or what it means to us when we answer these questions. So what it means to us when we answer these questions. The dependent variable is what we are measuring and the independent variable is what we are willingly changing, while the control variable is what is the same with regards to those different compounds. What is similar between those compounds? It can be functional group, it can be molecular formula, so on and so on. So independent variable, what is it that we are willingly changing? We are changing the branching because in this investigation, we're investigating the effect of branching on physical properties. So the answer to 3.2 is branching. Branching is our independent variable because that is what we are willingly changing in order to measure its effect on physical properties. 3.2. What about 3.3? Explain why these 3 organic compounds are called structural isomer. So structural isomer is same molecular formula but different structures. As you can see, well, it is even said to us that 3 structural isomers with the molecular formula C6H14. So they have the same molecular formula. They have the same molecular formula, which is C16H14. So same molecular formula, but different structures. Basically, we just given the definition of structural isomers here, right? Same molecular formula, but different structures. So that is 3.3. Let's take a look at 3.4. 3.4, write down the type of intermolecular forces that are present between molecules of these isomers. So let's take a look at our compounds A, B, C. A, B, C are hydrocarbons. They only contain hydrogen and carbon. So which intermolecular forces exist between in the hydrocarbons? It is London forces. London forces, it is the intermolecular force that exists in hydrocarbon. But in, let's say for instance, ketone, which intermolecular forces exist in ketone? London forces exist in ketone. Let's look at aldehydes. London exists. Carboxylic acids, London forces exist. So London forces exist in all our homologous series, right? But it's just that alcohol, for instance, it has London force and on top of that hydrogen bonding. But hydrocarbons, we only have London force, right? So when we say that alcohol has hydrogen bonding, which is stronger than dipole. Yes, it does have hydrogen bonding, but it also has London forces, right? I just thought that would be important to note. That is 3.4. Let's take a look at 3.5. Explain the difference in melting points between molecules A and B. So let's take a look at A and B. Let's take a look at A and B. So A, well, let me just show you something. We have 1, 2, 3, 4, 5. Then a carbon on the second carbon. Okay, and then that is A. And then B, we have 1, 2, 3, and then let's make these 4. Okay, so let's find our longest chain here because it seems like there's a lot going on. Let's take these as our longest chain. If we take that as our longest chain, then we have 2 branches there. Okay, so take a look at compound A and take a look at compound B. How do they differ? We're supposed to explain the difference in melting points between A and B. You can see that B is more branched. B is more branched. That should be easy to see that B is more branched, right, compared to A. B is more branched. It is more spherical. So compound B will have weaker intermolecular forces. We have weaker intermolecular forces. So weaker IMF. And as a consequence of that, less energy is required. Less energy is required to overcome the intermolecular forces in B. And then as a consequence, she's gonna have okay, what are we basing this on? Are we basing it on investigation 1 or investigation 2? We will still reach the same conclusion, but the question is, should we talk about melting point or should we ever talk about a boiling point? I think we can talk about both, really. So it will have a lower melting point and a lower boiling point compared to A. Right, if you have weaker intermolecular forces, you have a lower melting point and a lower boiling point, but a higher vapor pressure. Okay, that is 3 point. Is that 3.5? Yes, it is. So carrying on, take a look at 3.6. So 3.6 for investigation 3. Okay, in our tables we don't have investigation 3 there, but it is totally fine. The vapor pressure measured at 25 degrees Celsius is shown in the table below. Okay, we don't know which is for which, we're just giving some numbers. But anyway, stories. 3.6, the question itself. Using the information of investigation 2 and investigation 3, match the correct vapor pressure with the appropriate molecule A to C. Write down the letters A to C below each other with the corresponding vapor pressure next to each other. Okay, and then 3.7, we're supposed to explain that. We're supposed to explain our answer in 3.6. So let's just answer 3.6. Well, I'm going to explain as I answer 3.6. So there's no need for me to write down 3.7 as I'm going to give the explanation as I write the answers to 3.6. So 3.6, we need to match those vapor pressures to either to A, B, C. Okay, so again, the higher the boiling point, the lower the vapor pressure. The higher the boiling point, the lower the vapor pressure. So what is the lowest vapor pressure here? The lowest vapor pressure is 211. 211. So it means that the compound with the highest boiling point will have this vapor pressure of 211. So let's go ahead and see. Which compound is that? It seems to be compound A because it has a boiling point of 60, and B and C have 58 and 50 respectively. So we can say that this is C. Okay, and then we're saying that the higher the boiling point, the lower the vapor pressure. So it means that the compound with the lowest boiling point should have the highest vapor pressure. So back to our table, C has the lowest boiling point, so it should have the highest vapor pressure. The compound with the lowest vapor pressure should have the highest boiling point, and that is clearly compound A. Compound A has a boiling point of 60. B and C have 58 and 50 respectively. So here, 211, that is compound A, as it has the highest boiling point. Back to the relationship we know to be true. The higher the boiling point, the lower the vapor pressure. So it means that the compound with the lowest boiling point should have the highest vapor pressure. They're inversely proportional to each other. So 319 is the compound with the lowest boiling point. When we go back to our table, it will be easy to see that C should be that compound, as it has a boiling point of 50, which is the lowest for the three. So this is compound C. Without doing any further work, it should be easy to see that the one we are left with should be compound B. So there we go. If a reaction starts with an alkene, then it is an addition reaction. And then if it ends with an alkene, it is an elimination reaction. And if the first condition or the second conditions are not met, then it is a substitution reaction. So this is how you can easily identify the type of a reaction by just looking at the compound it starts with or the product that you have. If it starts with an alkene, it is an addition reaction. If it ends with an alkene, it is an elimination reaction. And if either of those are not true, it is a substitution reaction. So let's see how we can use this to answer this question. So 4.1.1, identify the type of reaction represented by B. So take a look at reaction B. Does it start with an alkene? No, it does not. It starts with an alcohol. So it cannot be an addition reaction. Does it end with an alkene? Yes, it does. As soon as we see that, we know that it is an elimination reaction because it ends with an alkene. Right, those are the only two things we need to look at. If it didn't end with an alkene, then it would be a substitution reaction. That is 4.1.1. Let's take a look at 4.1.2. Identify the type of reaction represented by D. So again, does it start with an alkene? No, it does not. Bromoethane is not an alkene. And does it end with an alkene? It is not. It ends with an alcohol. So because the first condition is not met and the second condition is also not met, then we are saying that it would be a substitution reaction. Those are the only two things that we need to look at. Does it start with an alkene? Does it end with an alkene? If that's not the case, then it is a substitution reaction. So there we go. That is 4.1. Let's take a look at 4.2. 4.2, we're supposed to write down 2 reaction conditions for reaction B. So reaction B, it's easy to see that we have a elimination reaction. So heat is a reaction condition for all elimination reactions. Heat is a reaction condition for all elimination reactions. Right, so heat is our first answer, right? As soon as we see a reaction condition and it is elimination, heat, we're going to think after that. So now let's find another reaction condition. So what is happening here? We have dehydration, right? We have an alcohol turning to an alkene. So we need a dehydrating agent, of which we can use a catalyst such as H2SO4. So we also need a catalyst as a reaction condition for this elimination reaction that we have. 4.2, let's take a look at 4.3 and 4.3.1. For reaction A, write down the name of the inorganic reactant. So reaction A, we are turning an alkene into an alcohol. Obviously, we need H2O to turn an alkene into an alcohol. And by our definition, H2O is inorganic because it does not contain carbon. So name of the inorganic reactant, it is water, right? Not H2O. The question is very specific. We are looking for the name of the inorganic reactant. And then 4.3.2, chemical formula of the catalyst used. Chemical formula, not the name, right? So don't confuse the two. Well, you know what they mean. Just be careful and not write a formula when they want a name, or write a name when they're looking for a formula. So here the chemical formula of a catalyst needed. We need H2SO4, right? H2SO4 is not always the answer to equation with regards to catalyst, right? It just happens that we have used it twice in this equation. Okay, 4.4.1. Let's take a look. For reaction C, okay, so reaction C, we are turning an alkene to a haloalkane, right? And then 4.4.1, use structural formula and write down a balanced equation. Okay, we're supposed to use structural formula. So this is our alkene with 2 carbons. How many bonds do we have? 1, 2, 3. So we need another hydrogen. And we can see that our product is bromoethane. So what are we adding here? We're adding HBr. And this should give us bromoethane. So the double bond gets broken, and it's just a matter of filling out the hydrogen and the bromo in one of those bonds. So there we go. I don't think there's any wrongdoing that we do in there. I think all is well, right? Quite an easy reaction. We have our alkene, we add a hydrogen and a halogen, so it is a hydrohalogenation addition reaction, and then this is our product. Okay, there we go. 4.4.1. Let's take a look at 4.4.2. So 4.4.2, explain why no water should be present during this reaction. Explain why no water should be present during this reaction. We are avoiding the formation of OH instead, right? If you have water, it's very possible that instead of having Br there, you might have OH. So that is what we are running from. Yes, we are trying to avoid the formation of the hydroxyl group, right? That is 4.4.2. 4.5, let's go ahead and take a look. So we are now concentrating on reaction E. Okay, let's see what the first question says. Type of reaction. Okay, so reaction E represents the conversion of the alcohol into organic compound X. So reaction E. Okay, so we start with an alcohol, as we can clearly see, and then we add what looks like an acid to get compound X. So something should come to mind when we talk about alcohol plus acid. This is clearly a esterification. So the answer to 4.5.1 is esterification. An alcohol plus an acid in the presence of a suitable catalyst will give you esterification, right? It will give you an ester. So type of reaction, esterification, right? So esterification. There we go. That is 4.5.1. Let's take a look at 4.5.2. Chemical formula of the catalyst used. We know what suitable catalyst we need in esterification. We need concentrated H2SO4. That's what we use in our esterification reactions. And then 4.5.3, structural formula of compound X. Compound X, I would assume, is the product formed. Let's go ahead and take a look. Okay, there we go. So our alcohol has 2 carbons. 1, 2. Okay, that's easy to see. And then our acid, let's go ahead and find out. We have 1, 2, 5, right? That's C multiplied by 3 there. So we have 1, 2 from the alcohol, and then we still have our oxygen from the alcohol. And then as long as it comes, and the carboxylic acid, we still have our double bond oxygen. And then 1, 2, 3, 4. So in total, 1, 2, 3, 4, 5. We have our 5 carbons from the carboxylic acid. So now, what we just need to do is to fill out the hydrogens everywhere else. I hope we're looking for the structure of the product and not the entire reaction, right? So there we go. Yes, maybe we should just do the reaction, the entire reaction, so that you can see where it is coming from, right? Maybe we should do the entire thing so that you can see where it is coming from. But this is the answer. This is our product. This is compound X, right? Let me show you where it is coming from. Either way, let me show you where it is coming from. So we're saying that our alcohol has 2 carbons. Yes, so it means that we have 1, 2, OH, hydrogen, hydrogen everywhere else. Okay, this is what we have, plus the carboxylic acid. Our carboxylic acid has 5 carbons, so it is 1, 2, 3, 4, 5. Well, let me put these a little bit to the right so that it will be easy to see when we remove our H2O, so that it can be easy to see when we remove our H2O. So hydrogen everywhere else. Hydrogen everywhere else. Okay. There we go. So what happens is that the alcohol loses the hydrogen and the acid loses the OH. Okay. And then that is why a byproduct or an inorganic product of esterification is H2O. Right, so we essentially losing this. We'll lose this part because water is removed from. Well, we get water when we add the two compounds. So that is why our product ends up looking like this. This is why our product ends up looking like that. Okay, so there we go. I hope you can see where it is coming from. Right. The alcohol loses a hydrogen and the carboxylic acid loses an OH. But anyway, stories. Let's take a look at the question that follows. Is it 4.5.4? I think so. We're looking for the IUPAC name of the compound. So how do we name an ester? Right, well, we started with the alcohol and then we finished off with the acid. So the alcohol here is ethanol, as it has 2 carbons. So we're going to have ethyl, and then the carboxylic acid is pentanoic acid, as we have 5 carbons. So we're going to have pentanoid. So the name of this ester is ethyl pentanoid. right? If the alcohol had 3 carbons, it would be propyl pentanoate. If the carboxylic acid had 4 carbons, for instance, it would be ethyl butanoate. That is how it works. First part of the name comes from the alcohol, how many carbons we have, and the second part of the name comes from the acid, how many carbons we have. That is 4.5, 4.6. Let's go ahead and take a look. So 4.6, reaction F takes place in the presence of warm concentrated sodium hydroxide. Use condensed structural formula and write down a balance equation for this reaction. Let's go ahead and take a look at reaction F. So reaction F, bromoethane to give us an alkene. Okay, so let's take a look there. In the presence of concentrated NaOH. So in the presence of concentrated NaOH, that's where elimination is going to take place. If it was in the presence of dilute NaOH, then substitution would take place. So let's go ahead and take a look at that. We start off with our bromoethane. Okay, so Br, hydrogens everywhere else. Okay, this is what we started with, and then plus NaOH. Okay, so what happens here is that, well, we are supposed to use condensed structural formula, not the way I'm doing it here. But let me just carry on with this for the sake of clarity. After doing this, then we're going to write it in the correct form. We're going to use condensed structural formula. Okay, so let's just carry on with this for the time being. So what happens here is that Na will bond with Br, and then OH will bond with the hydrogen removed, right? And then it means that our product, well, our byproducts, we're going to have NaBr plus H2O. Okay, that's how it goes. So let me show you. It means here that the products, we're going to have one double bond because now it is an alkene, hydrogens elsewhere, plus NaBr plus H2O. This is how the reaction takes place in terms of the structural formula. But our equation, we're supposed to use condensed structural formula. So let's go ahead and do that. This is just for the sake of clarity. So condensed structural formula, CH3, CH2Br. Okay, plus NaOH. And what does this give us? This gives us CH2, CH2. As you can clearly see, CH2, CH2. And then plus NaBr plus not NaOH, but H2O. Right, we have H2O there. So there we go. That is the condensed structural formula for reaction F. Okay, so 4.7, cracking. Let's take a look. We know fully well that this is still part of our syllabus, but it's one of those questions that they're not usually there in the exam. But let's go ahead and take a look at it. A large straight chained alkenes can be catalytically cracked to produce shorter chained alkenes and branched alkanes, which are more suitable for use in petrol. The reaction below indicates the catalytic cracking of octane. Okay, so octane, obviously we are expecting 8 carbons, and then here on the alkene we have 2 carbons. It means that on compound Y, which should be an alkane, we should have 6 carbons. So C6H14. That's what we expect compound Y to be. Right. So what does the question say? Write down the IUPAC name of compound Y. So 6,6, that is hex. So this is hexane. 4.7.1 is hexane. So there we go. hexane. And then 4.7.2 briefly explain why shorter chain alkenes and branched alkanes are more suitable for use in petrol than larger straight chain alkenes. So what do you think it is the answer to this question? Explain why shorter chain alkenes and branched alkenes are more suitable for use in petrol than larger straight chain alkenes. Right, maybe just to give you a hint, think about intermolecular forces, energy required, so on and so on. Let me know in the comments what your answer to this question is. The following apparatus was used by a group of learners in an investigation to find out how surface area affects the rate of reaction between excess solid magnesium ribbon and dilute nitric acid with a concentration of 0.05 mole per decimeter cube. During the reaction, the gas formed is collected in the measuring cylinder. The balance equation for the reaction is given to us right here. The summary of the investigation is tabulated before. So let's take a look. We have experiment 1 and experiment 2, where the mass of magnesium is the same. What is different is the state of division, as we are investigating the effect of surface area. The results for experiment 1 are plotted on the graph below. We can clearly see the graph here where the results are plotted. On the x-axis we have the time, and on the y-axis we have the volume of gas produced. Okay, let's take a look at our equations. The first question, 5.1, besides the mass and the volume of the reactants, give one other variable that must be kept constant during this investigation. Okay, so besides the mass and the volume of the reactants, we also need to keep the temperature constant. So the answer to 5.1 can be temperature. Why do we need to keep the temperature constant? Temperature affects the rate of reaction. So if you don't control the temperature, then your results will not be conclusive. You're not going to know whether your results are influenced by the state of the division or they're influenced by the temperature. So we need to keep all the other variables constant. We need to control them, hence control variable, and then have a fair test. Okay, that is 5.1. What about 5.2? Write down the dependent variable in this investigation. Well, the dependent variable is essentially what we are measuring, right? We are taking a look at the effect of state of division on the rate of reaction. So what you're measuring here is rate of reaction. It is our dependent variable. It is depending on that which is changing the state of division, which is our independent variable. Okay, 5.2. Let's take a look at 5.3. Use the graph to calculate the average rate of the reaction in centimeter cube per second between 2 and 2.5 minutes. Okay, let's go to our graph. So between 2 and 2.5 minutes, 2 minutes is 120 seconds. Okay, so let's take a look. This is 100, this is 150. 1, 2, 3, 4. So one block represents 10 centimeters. Oh, well, 10 seconds, not centimeters. So 1, 2. So 120 seconds should be here. This is where we have 120. 2 to 2.5 minutes. 2.5 minutes, that will be 150 seconds. So it's just 2 minutes plus half of a minute, which is 30 seconds. So 120 and 150 seconds. All right. So let's go ahead and find the corresponding y values. So let's go up. That is 120 seconds. And this is 150 seconds. And then we can extend this line. So that we can read off our value accurately. Okay, we just don't want to use our naked eye here. We want to take accurate measures. So there we go. So the rate of reaction. So rate of reaction will be equals to the change in the volume divided by the change in the time. Right? Why are we using change in the volume? We are given the SI unit we are supposed to use for rate of reaction is centimeter cube per second. So I'm just respecting that. So let's go ahead and find the gradient. We need to read off these values here. So from 40 to 50, we have 1. We have 1, 1, 2, 3, 4, 5. So it means that one block is 2 units. This will be 42, 44, 46, 48, 50. So it means that here at 120 seconds, we have 42. And at 150 seconds, we have 48. So the change in the volume, we're going to have 48 minus 42 divided by 150 minus 120. Okay, there we go. So let me just put that in my calculator. 48 minus 42 divided by 150 minus 120, that is 0.2. So we have 0.2 centimeter cube per second. There we go. That is the average rate between those 2 points. Okay, that is question 5.3. Let's take a look at 5.4. So 5.4, will the rate of the reaction at 250 seconds be greater than, less than, or equal to the rate of reaction in question 5.3? Give a reason for the answer. So in 250 seconds, it is going to be less than. It is going to be less than. Okay. Why do we say that it is going to be less than? Because as the reaction progresses, of which in our case it is not reversible, as you can see, the amount of reactants gets smaller and smaller. And as we have less number of moles, we're going to have less effective collisions. So we expect the rate of reaction to actually decrease. 5.4. 5.5. Predict how the gradient of the graph for experiment 2 will compare to that of experiment 1. So in experiment 2, we have ribbon as one large piece. And then in experiment 1, we have 5 smaller pieces. So the rate of reaction in experiment 1, we expect it to be higher than that in experiment 2. But what is the question saying? The gradient for the graph for experiment 2, it will decrease. The gradient will decrease in experiment 2 because the rate of reaction will also decrease. And yes, the rate of reaction depends on the gradient. If the gradient is very steep, then the rate of reaction is very high. Okay, that is 5.5. 5.6. 5.6. Calculate the mass of magnesium metal that remains in the conical flask when the reaction stops. Assume that the molar volume is 24 decimeter cube per mole. So the molar volume is 24 decimeter cube per mole at room temperature. Okay, fine. Let's go to our equation. Right, our equation, we have magnesium plus HNO3, and then we get in magnesium NO3 2. This 2 is here, it's not there. NO3 2 plus H2. Okay, this is the reaction we have. What is the mass of magnesium that you start with? Because it seems like here we are looking for the mass that is remaining. We start with a mass of 2 grams for both reactions. We start with a mass of 2 grams. So we are bound to use that. So what is the mass of the remaining magnesium at the end of the reaction? How can we possibly do that? Well, we have a graph that shows us the volume of gas produced, right? So what we can do, we can find the number of moles of the gas produced. With the number of moles of the gas produced, we can find the number of moles of magnesium used. with this number of moles of magnesium used, we can find the mass used consequently, and with the mass used and the mass initial that we have, we can find the mass of magnesium that remains. Okay, so these are the steps that we need to take. I keep emphasizing that with this kind of questions, you need your plan fully laid out before you can put pen to paper. Right, everything just becomes extremely simple if you know what you're going to do, when and why. So go ahead and do that. Number of moles of gas produced. We are given our graph, so we need to see where our graph ends here. And can we say that it ends here? I think, yeah, from there on until forever, essentially, our gradient is zero. So we have reached the end of our reaction. So let's take this part. Okay, let's take this part. This is where our reaction ends. Okay, and then we're supposed to extend the line and read off the volume from the graph. So this is the beautiful, well, a beautiful tool, but this is the interesting thing about these questions. You are always given an experiment, and you are being a scientist. Essentially, you are answering these questions in real time. You've never seen it before, but you have all these skills that you learned, which you need to apply. Okay, so let us see what happens here. Let me join these two lines so that we can read off the value. Okay, I think it will be easy to see here that the volume of gas produced is 60 centimeter cube. Okay, so we will say that number of moles is equals to V divided by Vm. Right, we've said that we're going to do that. We're going to calculate the number of moles of hydrogen gas, of which V is 60 times 10 to the minus 3. That times 10 to the minus 3 converts centimeters to decimeters cubed. I must emphasize, because when you're converting centimeter to decimeter, it's not the same thing as you converting centimeter cube to decimeter cube, right? And then the Vm, it is given to us as 24. Okay, so let's take a look. 60 times 10 to the minus 3 divided by 24. This is 0.0025 moles. So this is the number of moles of the gas produced, hydrogen gas. So now the number of moles of hydrogen gas is to the number of moles of magnesium. We have a 1:1 relationship, right? The balancing coefficients is 1:1. So here, the number of moles of magnesium should also be equals to 0.0025 moles. So there we go. We have the number of moles of magnesium that were used. So we can go ahead and calculate the mass of magnesium. So the mass of magnesium that was used will be the number of moles multiplied by the molar mass. The number of moles is 0.0025. The molar mass of magnesium is 24. So we're going to have multiplied by 24, which is equals to 0.06 grams. So not much of that magnesium was used. So the mass of magnesium that remains will be equals to the mass of magnesium that we started with, 2 grams, minus that which was used, 0.06. So we end up having the mass of magnesium that remains being equals to 1.94 grams. There we go. When the equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that opposes the disturbance. That is 6.1 Chartelie's principle, and we're going to use that to answer 6.2. Hydrogen gas is prepared by the reaction of methane and steam, as shown in the following balance equation. We can clearly see that we have methane, H2O, to form the hydrogen gas and carbon monoxide. Okay, and then the question is saying 6.2.1, how will the following changes affect the yield of hydrogen gas? Adding more methane. So in our reaction, you can clearly see that CH4 is one of the reactants. So if you increase the amount of CH4, the forward reaction will be favored so that CH4 is used up. The system reinstates a new equilibrium by favoring the reaction that opposes the change. So 6.2.1, adding more CH4, more methane, would increase the yield of H2. So it increases the yield of hydrogen gas. It increases the yield of hydrogen gas. Why is that so? Per Le Chatelier's principle, when there's a disturbance in a closed system, the system reinstates a new equilibrium by favoring the reaction that opposes the change. We have the amount of CH4 increasing, so the system will favor the forward reaction so that CH4 can be used up, and as a consequence of that, the amount of hydrogen gas produced would increase. And then 6.2.2, a decrease in the volume of the container. So this is what we need to understand. A decrease in the volume means an increase in the pressure, right? So there's an increase in the pressure in our system. How will the system reinstate the new equilibrium? It wants to decrease this pressure. And how does it achieve that? How does the system decrease pressure? It favors the reaction that leads to less number of moles of gas. Okay, but if you take a look at our reaction, we can see that we have methane as a gas, H2O as a gas, carbon monoxide as a gas, and hydrogen gas as a gas. So we need to take a look at the left hand side and at the right hand side, the products and the reactants. In the products, we have 4 moles of gas, right? 3 from hydrogen gas and 1 from carbon monoxide. And then on the reactants, we have 2 moles of gas, right? 1 from methane and 1 from H2O. So it means that if the volume has been decreased and the pressure has went up and we want to decrease the number of moles of gas, then we need to favor reverse reaction. We need to favor reverse reaction because the reactants have less number of moles of gas compared to the products. So in this case, the yield of hydrogen gas would decrease. So we have decrease in the yield of hydrogen gas. And why is that so? For the reasons I just gave, right? We are decreasing the volume, the pressure increases. The system wants to reinstate the equilibrium by favoring a reaction that opposes the change. Since we've increased the pressure, the system wants to decrease the pressure. So reverse reaction will be favored because it leads to less number of moles of gas, hence less pressure. So that is 6.2.2 right there. Okay, let's take a look at 6.3. The sketch graph below shows the changes in the number of moles of methane, steam, and carbon monoxide as the reaction proceeds for the preparation of hydrogen gas in a 2 decimeter cube container. Okay, 6.3, write down the reason why there is no change in the number of moles of each of the gases between T1 and T2. Okay, we can see that the number of moles of all those gases between T1 and T2 remains the same. There is no change. Why is that? That is what we need to explain. The reaction has reached chemical equilibrium. The rate of forward reaction is equals to the rate of reverse reaction. So here we just reached chemical equilibrium. That is why we see no change in the number of moles of the gases. Okay, 6.3. Let's take a look at 6.4. 6.4 says, use the information on the graph and calculate the equilibrium constant Kc for this reaction at temperature T. Okay, there we go. So that table, I think that table takes away from chemistry because most people can sketch that table, the feelings and values, but they don't really understand what is going on. You can actually answer these questions in the absence of tables, right? But most people use a table. So let's just go ahead and do that also. What do we start with? Okay, let's have our methane gas, CH4, and then H2O, carbon monoxide, and then the balancing coefficient of hydrogen gas is 3. And then this is the initial number of moles. This is the change, number of moles at equilibrium, and the concentration. So let's take a look at our graph. We can see that initially at t is equals to 0, we start with 1.4 number of moles of methane. So this is 1.4. And then that of H2O is 1.2. So we have 1.2. Carbon monoxide starts at 0, same as hydrogen gas. Okay. And then take a look at this at T2 or T1. When we have reached our equilibrium, we find that the number of moles of carbon monoxide is 0.6. The number of moles of carbon monoxide at equilibrium. So we have 0.6. So clearly, the forward reaction was favored, right? We have more products than we had initially. So it means that here there was an increase of 0.6, right? Meaning that for H2O, there was a decrease of 0.6 as the balancing coefficient is 1:1. If the balancing coefficient was, let's say, maybe 2:1, and then carbon monoxide is 1 and H2O is 2, then we would have minus 0.6 multiplied by 2. But here it is just 1. And then minus 0.6 also, because it goes down. And here we have plus 0.6 multiplied by 3. 0.6 multiplied by 3. Right, we are multiplying by 3 because of the balancing coefficient. Right, so this is 1.8. So 1.4 minus 0.6, that is 0.8. And then 1.2 minus 0.6, that is 0.6. And then 0 plus 0.6, 0.6. 0 plus 1.8, that is 1.8. So we have the number of moles at equilibrium. We need to find the concentration by dividing with 2 decimeter cube the volume of the container. If we do that, 0.8 divided by 2, 0.4. 0.6 divided by 2, 0.3. 0.6 divided by 2, once more, 0.3. 1.8 divided by 2, that is 0.9. We have the concentrations at equilibrium. We can go ahead and find Kc by saying that Kc is equals to the products divided by the reactants. Carbon monoxide, hydrogen gas to the power 3. The power is coming from the balancing coefficient. And then CH4 multiplied by the concentration of H2O. So there we go. The concentration of carbon monoxide is 0.3. That of hydrogen gas is 0.9. And we take that to the power 3. Everything divided by methane. 0.4 multiplied by water, which is 0.3. So we put that in our calculators. Let me just do that real quick. 0.3 multiplied by 0.9 to the power 3 divided by 0.4 multiplied by 0.3. And then I get 1.82. So 1.82. Right, that's it. We don't have an ISI unit for Kc. So there we go. That is the Kc. That is the equilibrium constant for this reaction. That is 6.4. So tell me, here's a question for you. 6.5. The temperature T is decreased. The temperature T is decreased. How will this change affect the Kc value for the above reaction? Right, only increase, decrease, or remain the same. The temperature T is decreased. How will this change affect the Kc value? Let me know in the comments what you think the answer to this question is and why. Here we go. H2SO4 is a strong acid. And why do I say that? It ionizes completely in water. That is the answer to 7.1. H2SO4 is a strong acid. It ionizes completely in water. That is the reason. And then taking a look at 7.2, write down the formula of the conjugated acid-base pair in step 2. Okay, so let's take a look at what is happening here. The balance equations below represent the ionization of water, of sulfuric acid in water. Step 1 and step 2. So what we need to give is the acid-base conjugate pairs in step 2. So let's take a look at the reaction. We have HSO4 minus plus H2O. This gives us H3O plus SO4 2 minus. So acid-base conjugate pairs. Alright, let's start with HSO4. In the products, we have SO4 2 minus. So clearly we can see that HSO4 minus donates a proton to become SO4 2 minus. So because it is a proton donor, it is an acid. And then what is left after an acid donates a proton is the conjugate base. So there we go. And then on the other hand, H2O will be our base as it accepts a proton to become H3O plus. So this is a conjugate acid, right? It's the ion formed after a base accepts a proton. So our acid-base conjugate pairs, HSO4 minus and SO4 2 minus, that is an acid-base conjugate pair, and H2O with H3O plus. That is how we answer 7.2. 7.3, H2SO4 is diprotic. Write down the meaning of the term diprotic. So let me show you what we mean when you say H2SO4 is diprotic. So H2SO4 can give us 2H plus SO4 2 minus. So for one H2SO4, it can donate 2 protons. That's why we're saying that is diprotic. For instance, HCl that can only donate 1 proton would be called monoprotic, because for one HCl we have 1 H plus, but with H2SO4 clearly we have 2 H plus, so we refer to it as being diprotic. There we go. That is 7.3. Let's take a look at 7.4. 7.4, write down the formula of the ampholyte in the above reaction. So an ampholyte, an amphiprotic species, is a substance that can act as both an acid and as a base. So take a look at step 1. Step 1, we have H2SO4, which is our acid, and the conjugate base is HSO4 minus. So in step 1, HSO4 minus acts as a base. Take a look at step 2. In step 2, HSO4 minus donates a proton to become SO4 2 minus. It acts as an acid. So clearly it can act as both an acid and a base. So what do we refer to that as? It is an ampholyte. So the answer to 7.4, we have HSO4 minus. Let's take a look at 7.5. An impure sample of potassium hydroxide pellets with a mass of 11.2 grams is added to 0.09 mole of sulfuric acid with a volume of 600 centimeter cube. It reacts according to the balance equation given below. There we go. And then 7.5.1, calculate the initial pH of the sulfuric acid used in this reaction. Okay, so what is the pH of the sulfuric acid used? It ionizes to form 2H plus SO4 2 minus, as I demonstrated below. You will see in just a few minutes, few seconds probably, why I'm doing that. So let's take a look at the given information. We have the number of moles of sulfuric acid and the volume. We can find the concentration, right? We want to find the concentration so that we can use it to find the concentration of H plus and therefore find the pH. So we'll say that concentration is number of moles divided by volume. Number of moles 0.09. The volume is 600 centimeter cube divided by 1000 in order for us to convert it to decimeter cube. We will get 0.6. So 0.09 divided by 0.6, that is 0.15. So we have 0.15 moles per decimeter cube. So as we can clearly see from this equation, H2SO4 is to H plus, we have 1:2. So if the concentration of H2SO4 is 0.15, the concentration of H plus will be 0.15 multiplied by 2, which is 0.3. So we have the concentration of H plus. pH is equals to minus log of H plus. So we're going to have minus log of 0.3 being equals to, so minus log 0.3, 0.52. So the pH is 0.52. There we go. We have the initial pH of the acid in the reaction. 7.5.2. The percentage purity of the potassium hydroxide pellets used is 80%. Calculate the number of moles of pure potassium hydroxide that react with H2SO4. Right. The mass of the impure sample is 11.2. We want to calculate the number of moles of pure potassium hydroxide. The question we're asking ourselves is, what is 80% of 11.2? So we have the mass of pure, which will be 11.2 multiplied by 80%. Right. So 11.2 multiplied by 80% is 8.96 grams. So this is the mass of potassium hydroxide. That is the mass of the pure potassium hydroxide. So with this mass, we can then find the number of moles with ease. The mass is 8.96. The molar mass of potassium hydroxide is 56. And if you put that in your calculator, you shall get 0.16 moles. So these are the number of moles of potassium hydroxide that react with H2SO4. Okay, 7.5.3. Determine which reactant is in excess and hence state whether the final solution is acidic, basic, or neutral. Right. What a beautiful question. Let's take a look. The number of moles of H2SO4 that we have is 0.09. The number of moles of potassium hydroxide that we have is 0.16. These are the number of moles that we have. So let's perform a test. If these number of moles of H2SO4 are to react completely, how many number of moles of potassium hydroxide would be required? Right. So let me show you how we tackle this. So the number of moles of H2SO4 is to the number of moles of KOH, that is 1:2. We are getting that from the reaction, the balancing coefficients. So if 0.09 of H2SO4 is to react, we would need 0.18 moles of potassium hydroxide. Right. So these are the number of moles that we need for H2SO4 to react completely. But as you can see, what we have is less than that. So that tells us that KOH is our limiting reactant. So H2SO4 is in excess. Right. So if H2SO4 is in excess, then the final solution should be acidic. There we go. Is the reaction that occurs in this cell spontaneous? Write down only yes or no. Give a reason for the answer. That is 8.1, Prelim 2023. Let's take a look and see what is happening. So a galvanic cell is set up using an Mn and an unknown metal X. The initial EMF measured under standard conditions is 1.05 volts, as we can clearly see there. The electrons flow from the Mn to metal X in the external circuit, right? And then 8.1 is the reaction that occurs in this cell spontaneous. Yes, it is. And why do we say so? EMF is greater than 0. If the EMF in this cell is greater than 0, then the cell is spontaneous. This reaction does not need any external energy for it to occur, right? Does not need anything. It does not need power supply, unlike in an electrolytic cell. That is 8.1. Taking a look at 8.2, which electrode X or Mn is the anode. Okay, so the answer to this question is here in this statement. The electrons flow from the Mn to metal X in the external circuit. So we need to recall our basics with regards to a galvanic cell. The electrons, they flow from the anode to the cathode in the external circuit. So if they flow from Mn to metal X, then Mn should be the anode, and then the metal X should be the cathode. Clearly, the electrons flow from Mn to metal X in the external circuit. So Mn is the anode and X is the cathode. Okay, we just applying the basics here. That is 8.2. 8.3, use calculations to identify metal X. So we are given the initial EMF, which is said to be 1.05. But obviously, using our table of standard reduction potentials, we can obviously find the potential at the anode, which happens to be our cathode. So at the cathode, this is where we have our metal X. This is where we have X. And then at the anode, that's where we have Mn, like we've deduced. So now let's go down and look for our table of standard reduction potentials. We can use table 4a, we can use table 4b. All is well, right? There's no difference really. So let's go ahead and look for Mn and see where it is. So let's take a look. Mn, where do we find it at? We have Mn right there. So the reduction potential at the anode is minus 1.18. Okay, and then we know that the EMF of the cell is given by the reduction potential at the cathode minus the reduction potential at the anode. Okay, so the reduction potential at the cathode, that is where we have our metal X, right? So the potential of X. And then at the anode, we have minus 1.18. So 1.05 will be equals to the reduction potential at X plus 1.18. Okay, so the reduction potential at X will be equals to 1.05 minus 1.18. So that's more like saying 5 minus 18. So we get minus 0.13 volts as our reduction potential at the cathode. So still sticking to the table of standard reduction potential, it should be easy to see that at the cathode, if the reduction potential is minus 0.13, we must have PB. We can clearly see there that the reduction potential is minus 0.13. So right, X is PB. We can clearly see that. Right, that is 8.3. Let's take a look at 8.4. Right, 8.4.1. Write down the two standard conditions for this cell. Okay, we know fully well that we need the temperature to be 25 degrees Celsius, right, or 298 kelvins. That's one of the conditions that we need. Another condition we need is concentration to be 1 mole per decimeter cube. These are our standard conditions. Okay, 8.4.1. 8.4.2. On the other hand, we are looking for the cell notation. Okay, so obviously we know that we have what is happening at the anode, the salt bridge, and what is happening at the cathode, essentially. So at the anode, we have Mn, like we talked about, right? So we're gonna have Mn, the metal, and then Mn to the 2 plus the salt bridge, and then Pb to the 2 plus, and then we have Pb. Okay, we can show the states here that is a solid, that is also a solid, and here we have aqueous solutions, right? We can show the states. Yeah, we can even go further to show the concentration also, that the concentration of these aqueous solutions should be 1 mole per decimeter cube. Okay, that is 8.4.2. 8.4.3, reduction half reaction. Reduction half reaction. So reduction occurs at the cathode. That's where we have a gaining of electrons. So we're gonna have Pb to the 2 plus, that gains 2 electrons to become Pb. There we go. Nothing complicated there whatsoever. That is the reduction of reaction. And then if the question was looking for the oxidation of reaction, we would have Mn giving off 2 electrons to become Mn to the 2 plus 2 electrons. And then we can sort of combine these two into overall cell reaction, right? To get Mn plus Pb to the 2 plus, giving us Mn to the 2 plus Pb. This will be the overall cell reaction. But anyway, stories. Write down the energy conversion that takes place in this cell. It is an electrolytic cell. So we have electrical energy to chemical energy. Electrical energy to chemical energy. We can also see that by the presence of a power source, we have electrical energy being supplied to the cell. And that electrical energy is then converted to chemical energy. 9.1, let's take a look at 9.2. At which electrode A or B will pure copper be deposited? 9.2. Right, so pure copper, it will get deposited at the negative electrode, meaning that the answer to 9.2 should be B. Let me show you why it will get deposited at the negative electrode. Take a look at this. We have CuCO4, which will break down to form copper 2 plus SO4 2 minus. This is a positive ion. This is a negative ion. The positive ion will get attracted to the negative electrode, which is B, and that's where a reduction is going to take place. So that is why I'm saying that the pure copper will be deposited at the B, because it is negative, and the copper 2 plus will be attracted to the negative electrode, as positive and negative attracts. 9.2. Let's take a look at 9.3. Write down the half reaction that takes place at the anode. At the anode, we have oxidation of copper, right? So we're going to have copper turning to copper 2 plus 2 electrons at the anode. This is at the electrode A. At the electrode A, we're going to have copper becoming copper 2 plus 2 electrons. There we go. Let's take a look at 9.4. How will the gradient of the graph be affected as the reaction is allowed to proceed until completion? Right, only increase, decrease, or remain the same. So let's take a look at what's happening here in more detail. The diagram below represents the purification of copper ore to pure copper. The cell also contains zinc, silver, and platinum impurities. Right. The graph shows the initial relationship between the mass of copper deposited versus the time. So back to our question, how would the gradient of the graph be affected as the reaction is allowed to proceed until completion? Well, the gradient of the graph is not going to change. The gradient of the graph is not going to change. As oxidation occurs, reduction occurs. So we're never going to reach a point where the mass of copper deposited well, the rate at which the mass of copper deposited goes down, we're never going to reach such a point or a rate where it increases. The gradient will remain the same throughout until completion. Right. 9.5. Refer to the relative strength of reducing agents to explain why zinc will not be deposited at the cathode. Why zinc will not be deposited at the cathode. Why zinc is not going to be deposited at B. So let's take a look at what is happening here. The question says that we have some impurities, which happens to be zinc, silver, and platinum. But in our question, we are only interested, so let me just say in 9.5, we are only interested on zinc and copper. Why is zinc not being deposited at the cathode? Why is it copper that is being deposited at the cathode? So it means that we have, as our ions in the solution, we have zinc 2 plus and copper 2 plus. One of these two is to be deposited at the cathode where reduction is going to take place. So between zinc 2 plus and copper 2 plus, what is the stronger oxidizing agent? Because the stronger oxidizing agent is what's going to get deposited at the cathode. The stronger oxidizing agent is what's going to get deposited at the cathode. So what do we need to do? We need to go to a predict table and see which one it is between zinc 2 plus and copper 2 plus. The question says, why is zinc not being deposited at the cathode? So obviously we already have our answer, but I'm just trying to show you where it is coming from. Copper 2 plus is a stronger oxidizing agent compared to zinc 2 plus. Let's go to our table so that it can be easy to see. Right. So our table, standard reduction potential. Okay, let's take a look at, let's use 4A. It doesn't really matter which table we use, by the way. So take a look. Increasing oxidizing ability as we go down. So let's look for zinc and copper 2 plus. Okay, so where is zinc? Where is copper 2 plus? This is copper plus. We're not looking for that. We're looking for copper 2 plus. We have copper 2 plus right here. No, that is actually not the one we're looking for, because we're looking for the one that will accept 2 electrons to form copper. This is the one you're looking for. This is the copper 2 plus you're looking for. So be very careful when you're using this table. You just don't find copper and take it as it is. You have to take a look at exactly what you are dealing with. Okay, so we're saying that copper 2 plus is a stronger oxidizing agent. So we must find zinc. I was starting to get worried a bit. Here we have a zinc 2 plus, but look at my arrow. My arrow is going the wrong direction. The arrow is supposed to be pointing up, as you can clearly see here on our table. So clearly copper 2 plus is a stronger oxidizing agent compared to zinc. So the answer to 9.5, which is saying refer to the relative strength of reducing agents to explain why zinc will not be deposited at the cathode. Zinc will not be deposited at the cathode because copper 2 plus is a stronger oxidizing agent, right? And zinc 2 plus is a stronger reducing agent. Therefore, okay, so that is the reason why it is copper 2 plus that's going to be deposited at the cathode and not zinc 2 plus. Okay, that is 9.5. Let's take a look at 9.6. Maybe I need to erase this going to 9.6 so that I can have a bit of space. So let's do that. Back to our diagram and back to 9.6. So 9.6, when the current flows for 30 minutes, 15 grams of copper was deposited at one of the electrodes. Okay, and then 9.6.1, calculate the number of moles of copper deposited. Well, quite an easy equation because we are given the mass. So we are really sticking to the basics. Number of moles is equals to the mass divided by the molar mass. Right, and then the mass is 15 grams. The molar mass of copper, that is 63.5. When you put that in your calculator, you get 0.24 moles. Right, it's quite a strange equation, right? Because we're just calculating the number of moles, no trickery whatsoever. 9.6.1, let's take a look at 9.6.2. Determine the number of moles of electrons that flows through the circuit while 15 grams of copper is deposited. 1 mole of copper gives us 2 moles of electrons. Right, it sounds very wrong to say 2 moles of electrons, but we can see the relationship here. For 1 copper atom, we have 2 electrons. So if we're saying that the number of moles of copper, well, we're saying copper is 2 electrons. If we're saying it is 0.24, then that of electrons should then be 0.48 moles. So there we go. That is question 9.